Hello everyone, I'm Nur Rashidah binti Muhammad Zaki and I'm thrilled to be your moderator as we begin a deep dive into the earliest chapters of mathematical thought. To ensure this remains a great place for discovery and discussion, please review our community rules. Remember, curiosity is the only prerequisite here. Let, let the historical calculations begin. Why we should study ancient math? We often take our modern Hindu-Arabic Western for granted, but every equation we write today stands on the foundations laid by ingenious ancient civilizations. This forum is dedicated to exploring how these cultures counted, calculated, and conceptualized the universe using unique and sometimes baffling methods. The contrast between the simple symbols of the past and the complex problems they solve, from constructing the pyramids to predicting eclipse, reveals just how profound human intellect has always been.
Okay.
We are incredibly fortunate to be joined by a panel of experts who will be leading our discussions through this incredible historical journey. The first panel is Fong Sherman. Her focus is on Greek and Egyptian mathematics, offering insights into logic and formal proof. The second one is Lin Jingjie, an expert on the Roman and Babylonian mathematics systems, who will guide us their advanced algebra and astronomy. And Nur Mushidah Penti Muhammad Zaki, as your moderator today, I will explain about Mayan mathematics. Every number, every number system is a special kind of code. This code has two main things. Firstly, symbols, the digits we write down, and a set of rules. Our modern system, base 10, uses 10 symbols from 0 to 9 and follows a crucial rule called positional notation. It means the place of a digit matters 2 in 20 is different from 2 in 2. This only works because we have the concept of 0 to act as a placeholder. As we explore ancient history, we will see systems that ignore these place matters rules, like the Romans, which are additive systems, and others that invented a different base, like the Babylonians using base 60. Understanding these basics, understanding these basic differences will let us appreciate the incredible genius and the frustrating limitations of ancient mathematics. Following the introduction on different types of numeral systems, could Shermin start us off by explaining the key characteristics and principles of the ancient Egyptian numeral system and also the Greek numeral system?
Thank you, Mushida. To answer this question, I will start with the ancient Egyptian numeral system. So the Egyptian number has a few characteristics. First of all, it is hieroglyphic. It is base 10, repetition for quantity. It is additive, and its written direction is not fixed. Furthermore, it is non-positional. So this two picture is a perfect example of Egyptian numbers. It is hieroglyphic because it uses symbol as representation. It is base 10 in nature as it changes unit after 10 repetitive symbol. It is addictive. It is addictive due to its system of adding up all the symbols of repetition. As in this picture, 3244 is represented as 3200 plus 40 plus 4. Lastly, this numeral system is non-positional because it is an addition of all the value. The value exists in the symbol, not the placement. It can even be written vertically or horizontally. Just remember that it's supposed to be read four faces. So I would like all of you to focus on this picture. As you can observe in the previous example, different symbol is used to represent the unit of tens, hundred, thousand, etc. in Egyptian mathematics. As a hieroglyphic system, there's a reason behind the symbol selection. Thus arises the question, what is the representation behind the numerals unit? To start, why does a stroke represent 1? This is because it is the most basic unit, like the ancient telemark system. Next, the heel bone is used to represent 10. Why? Because it represents a bundle. Now, why is this called a rope 100? According to research, rope was used for measurement in ancient Egypt. It is used to measure land after Nile flood, which is a common occurrence due to seasonal change. Following this, the larger unit they took on a more abstract representation. In the Egyptian culture, lotus flower represent creation, growth, and abundance, and also it blooms in large numbers, so it represents 1,000. This pointer finger is 10,000 because it symbolizes many tens of thousands. Tadpole is 100,000 because of its strong breathing ability. Lastly, this symbol is He. It is the god of infinity, hence it symbolizes a million. In ancient Egypt, this is an enormous number that is hard to imagine, so a divine symbol is used. Furthermore, I would like to illustrate the addition and subtraction in the Egyptian numeral system. So based on this picture, you can see that the first number is 365, the second number is 257. To do addition, you write all the symbols together and then you turn those symbols that exceed 10 into the next unit. So the total becomes 632. Similarly, the subtraction have a similar concept. If the symbol to subtract is not enough, right, you take the bigger unit, unravel it into 10 smaller units to subtract. So this demonstrates that the ancient Egyptian actually has a solid understanding of arithmetic. Next, for the Greek numeral system on the other hand has two numeral systems. The more widely used is Ionic or alphabetic. However, before they adopt this Ionic numeral system, they had an older acrophonic system. The acrophonic system is a numeral system where signs represent numbers using the first letter of the word for that number. So these three pictures show the letter used in the acrophonic system. While it looks functional, it has a big limitation when writing a large number. This system is additive in nature, so when a large number is written, it has many repetitive symbols is duplicated. While certain number can represent through combining acrophonic numeral, for those odd number between symbols, the representation is too long and troublesome. For example, the following pictures show the writing for 3807. You can observe there are many repetitive symbols and the additive process is very complicated. This causes huge inconvenience, hence it is replaced. The Ionic system, however, is easier and more widely used. This system uses 24 letters of Greek alphabet and 3 archaic letters, as you can see in this table. So it is also additive. Similarly, it is base 10 in nature. Yet you need to keep in mind that it used the alphabet to represent numbers, thus some may mistake them for words. To prevent this error, a small stroke mark was added to indicate the value was numerical, not textual. For example, this value is 154. Well, 1000 was indicated with a lower left mark like this. So this symbol is 5392. Hence, due to its sufficient alphabetic representation, the numeral writing becomes easier to read and understand.
Thank you, Shermin. Moving from the Egyptian and Greek systems, let's turn our attention to the Roman numeral system. We will move on to panel 2 to get more information on the key characteristics of the Roman numeral system and the Babylonian numeral system.
Thank you, Moshida, for the wonderful introduction. Now let us dive into Roman and Babylonian numeral system. Firstly, for Roman mathematics, its numeral system was a number system that expressed numbers collectively using letters. For example, the 7 Latin letters I, V, X, L, C, D, and M are employed to represent numbers by the ancient Romans. Each of these letters carries mathematical meanings in the Hindu-Arabic numeral system. For instance, the value of each letter can be seen view this picture below. I represent 1, represent 5, X represent 10, L represent 50, C represent 100, D represent 500, and M represent 1000. For example, the number 2 here is formed from 2i. This is because 1 plus 1 equals to 2, and in which the number 1 is represented through the letter of I. Let me take another example, which is 600 is represented by DC. In which 500 plus 100 with 500 represented by D and 100 represented by C. Besides, the numeral system is a non-positional system, unlike our modern base 10 system. There are two reasons behind this concept. The first reason is that each symbol of Roman numbers has a fixed values, which means that each symbol has the same value no matter it's written in the at the first place or the behind place. For example, 1 always represent I always represent 1 and V always represent 5. The value for the symbol will not change even when it's combined, such as VI equals to 6 and IV equals to 4. However, what changes is how it's combined, which is through addition and subtraction. Secondly, it doesn't have a place value. Compared to our modern base 10 system, a digit position always show its values. For example, the digit 3 in the number 3 is often referred to as 3 ones, while the digit 3 in the 30 is referred to as 3 tens. However, in Roman numbers, there are no place value. For example, X always represents 10, whether it's written in the first, middle, or last. The Romans used different symbols such as I, X, C, and M for each group of 10 or 100 to represent it. Hence, that's the reason why Roman numbers are a non-positional system, as their value don't depend on position, but on the combination and orders of symbols. So how does the combination of symbol change the value? Eventually, we can change a natural number into a Roman numeral by rearranging the letters. Let me take an example, which is the Roman numeral LX. The L represents the value of 50, while X represented the value of 10. Altogether, LX will represent 60, because 50 plus 10 each is equal to 60. In contrast, what if the Roman numeral is XL? It will be 50 minus 10, which is equal to 40. This is because the value X is placed before a greater value symbol, which is L. Thus, it will be subtracted from the numbers. Hence, from this example, we can clearly see that there are two basic rules for combining Roman numbers. The first rule is that if a symbol holding a greater value is placed after another symbol of greater or equal value, addition occurs. The second rule is that if a symbol of a smaller value is placed before a greater value symbol, subtraction occurs. Furthermore, there are other necessary rules guiding the Roman numerals. The first rule is when certain numerals are repeated, the number represented by them is their sum. For example, x will equal to 20 and xxx will equal to 30. However, it's been noted that no Roman numerals can become together more than 3 times. For example, we cannot write 40 as xxxx. This is incorrect. That's rule number 2. The rule number 3 is that the letters V, L, and D are not repeated. For example, we don't write VV for 10. This is wrong. Instead, we write X. X stands for number 10. Next, the rule number 4 is that only I, X, and C can be used as subtracted numerals. The example is showing by here, the 4, the 9, the 40 here only can be subtracted with this only this letter I, X, and C. Next is the rule number 5 is that multiply a number by a factor of 10,000, a bar will be placed over it. For example, the Roman will use it to represent large number more easily. For example, V with a bar above represent 5 multiplied with 1,000, which is equal to 5,000. So that is the example. Next, the last rule is that no Roman numerals for 0, because Romans didn't use 0 in their counting system. Their numerals always work with adding and subtracting symbols. Hence, that's the basic rule for Roman numeral system. In contrast, the Babylonian numeral system is different from the Egyptian and Roman system. They use a system for writing down numbers using symbols for singles, tens, and hundreds. This system is also known as the sexagesimal space 16 system, meaning that their number system was based on 60 instead of 10. In Babylonian mathematics, you can see that they use 2 main symbols shown in this picture, written in cuneiform on clay tables. A single wedge represents number 1, and a sideways wedge represent 10 to represent the numbers. Numbers were made by combining this symbol. For example, 3 single wedge. 3 single wedge here you can see represent number 3, and a side wedge, you can see here, there's a side wedge and 2 single wedge represent the number of 12. So it's actually a combination of the single wedge and also the side wedge. However, until 60, the symbols looks a bit different from others. You can look at the picture below here. What does it happen and why it's different from others starting from 60? This is because Babylonians were working on their way towards a positional system, which is totally different from Roman mathematics. So the Babylonian numeral system is actually a positional system in which the position of a symbol determines its value. Each position represents a power of 60, not 10. For instance, 60 here, the number 60 is written as a single wedge in the next positional place because it is 1 times 60 power by 1. It's like moving 1 place to the left. Similar to how 10 in our modern system means 1 in the 10th place. Therefore, 60, you can see the number 60 is written to be like number 1. You can see from the picture here, 60 is almost the same as the number of 1, but it's actually in the next positional place. As for 61, it's written as two single wedges, which means 1 times 60 with 1 times 1. It shows that 1 in the 60 place and 1 in the first place together, which equals to 61, as illustrated in the picture shown here. So from these 2 pictures, we can clearly see that the Babylonians had the concept of place value and the sexagesimal base 60 system compared to Roman mathematics, which was a major mathematical breakthrough.
Thank you, Joyce. I can summarize that the most crucial distinction among these ancient systems lies in their approach to place value. In short, Egyptian, Greek, and Roman math relied on repetition and addition. Babylonians math relies on position and a sexagesimal base, marking a significant leap toward modern number system. The Mayan numeral system, a positional planner, the ancient Mayan civilization developed one of the most advanced and sophisticated number systems in the world, distinct from those in Europe and the Middle East. The vigesimal base. Have you wondered why numbers from 11 to 19 have different naming scheme compared to say numbers from 50 to 59? Unlike 52, which is called 52, 50 plus 2, 12 is not called 22, 10 plus 2. This anomaly is present till 19. Why? Welcome to the vigesimal system, where the base for counting is not 10, but 20. It is as old as Mayan civilizations. Second one, simple symbols. The system uses only three core symbols to represent any number. A dot represents the value of 1, a bar represents to the value of 5, and a shell or stylus shape represents the value of 0. These symbols are thought to represent items that the Mayan people might have first used to count with, such as pebbles, sticks, and shells. In other words, 0 is represented by a shell, 1 to 4 are represented by dots. The Mayan wrote their numbers from top to bottom rather than from left to right. Multiples of 5 are represented by lines with extra dots by being added to complete the numbers as shown below. The purpose of mathematics in ancient history was primarily utilitarian and practical, focused on addressing the immediate organizational and physical needs of complex societies. But it also served crucial cosmological and philosophical roles, particularly in later Greek thought. Early civilizations like the Egyptians and Babylonians developed sophisticated arithmetic and geometry technique for essential tasks such as record keeping, architecture, trade, and calendar creation for agriculture and religious gathering. We have discussed the systems they use, but let's talk about purpose. Shermin, could you explain the fundamental difference in the application between ancient Egyptian and Greek mathematics? Where did each civilization choose to focus its mathematical energy?
Well, Mushida, to make it simple, Egyptian mathematics is practical, while Greek mathematics emphasizes more on its theoretical and philosophical aspect. Egyptian mathematics were utilized for many purposes. As mentioned, it was focused on solving practical and real-life problems. Its application can be observed through many historical artifacts. The right mathematical papyrus effective proves that mathematical skills were integrated into the ancient Egyptian daily life. In that paper, 84 different problems and calculations were presented that would have been used in different scenarios to solve practical difficulties of life. One of the biggest purposes is of ancient Egyptian mathematics is for record keeping. In ancient Egypt, those who could read and write were known as scribes. They are part of the nation's administration. They play a crucial role in managing supplies. The background information states that ancient Egypt distributed foods and goods as payment, which vary according to rank. Hence, the scribe mastered mathematical skills to ensure fairness and smoothness in ration distribution to support the nation's operation. Next, Egyptian mathematics is also used for architecture. As stated by Shuttleworth, the ancient Egyptians were excellent in arithmetic, astronomy, and geometry. We own many earliest findings of geometrical knowledge such as shape, length, and area measurement in ancient Egypt. They facilitate the knowledge to build monuments. One of the most famous monuments built is the pyramid. In the aforementioned Rhine mathematical papyrus, there is a section that records the calculation for the volume of a pyramid. The Egyptian employed to measure distance is in construction. Lastly, one of the greatest achievements of Egyptian mathematics is the creation of the calendar. The calendar we use in modern days is the Gregorian calendar, which consists of 12 months and 365 days. The Egyptian calendar is thought to be the precursor of the Gregorian calendar. It includes 12 months, with each month having 3 weeks and each week has 10 days, and 5 extra days for a total of 365. These days were divided into 3 seasons with 4 months each. However, they did not keep track of the year count because the year count resets as each pharaoh started their reign. Now, for the ancient Greek, it emphasized more on the theoretical aspect of mathematics. Rather than apply it in real life like the Egyptian, the Greeks used mathematics to unfold the reality and natural order in this world. Many Greek mathematicians were born in this civilization. For example, Euclid. He is generally viewed as the founder of geometry. He wrote the Elements. This book defined the basic concept of geometry, such as a line is a length without breadth. This concept dictates the whole discipline of geometry. Furthermore, there are also pioneers such as Pythagoras, Aristotle, Plato, and many more. They integrate mathematics with other disciplines like physics, engineering, astronomy, philosophy, etc. This integration leads significantly to academic and civilization development. It correlates to form a more wholesome understanding of this world. Therefore, the reason behind this world is discovered. Furthermore, Greek mathematics is utilized to foster deductive reasoning and encourage logical thinking. Ancient Greek mathematics delved deep into the theoretical concept behind mathematics. They encouraged logical thinking to search for proof behind the theory. They encouraged For example, Euclid demonstrated that truth can be proved from axioms. He established a deductive structure that became the foundation for future research. In this deductive approach, mathematicians reached conclusion through a chain of logical steps. Theo was also a pioneer in this field. He came even before Euclid. He is the first to use deductive thinking to derive mathematical theorem, and his work is still being studied and built upon nowadays. So to conclude, we can say that the Egyptian mathematics focused on practical application like the calendar, record-keeping architecture, whereas the Greek mathematics delved deeper into the reasoning behind it to understand this universe.
Thank you, Shermin, for sharing. Joyce, could you explain the fundamental difference in application between ancient Roman and Babylonian mathematics?
Sure, Roman mathematics was utilized for a more practical application, while Babylonian mathematics it was utilized for both practical and scientific purposes. Firstly, let's look at Roman mathematics, which was often utilized in areas such as trade and commerce, geometry, government and administration, and recording dates. So first, let's look at the number one. Firstly, Roman surveyors used geometry and a tool called the groma to measure land and build cities. It was an antique survey tool that they frequently utilized since the 4th century BCE in Mesopotamia. The groma was a cross-shaped wooden frame with plumb bones hanging from each arm. It is to survey straight lines and perpendiculars. It also allowed for simple measuring and for rectangular areas. Therefore, the Romans often used it to draw straight lines and right angles to make grid patterns for roads and streets. These skills also helped them to build roads, aqueducts, and new towns efficiently. Until now, these skills have been used by many modern cities in Europe and America by following the grid design for building cities and towns. Next, back in those days, the Romans were widely known for their engineering architecture, such as roads, homes, bathhouses, indoor toilets, and more. However, one of the most significant things that they built was these counting boards and hand abacus using Roman numerals only to record the results. They were used in trade and commerce. For example, they used counting boards and hand abacus to record intricate, complex, and extensive accounting of their trade. They also use it for counting monies, recording prices, calculating tasks and wages, while Roman numerals help them to add, subtract, multiply, and divide while trading. Next, in addition, it's also used for government and administration. Aside that, collecting and recording taxes, they also use it for counting citizens and soldiers. Back in those days, Roman soldiers were structured in a way that made counting manageable. They are structured in cohorts consisting of centuria, which is a group of 80 men, and comprise a legion of about 4,800 soldiers. Hence, when it comes to counting and tracking soldiers, it will be written down using Roman numbers. A centurion will be a commander of 80 men, therefore easier for them to monitor the soldiers and also tracking the soldiers. Furthermore, it's also used for recording dates. For recording dates, it's recorded according to a special calendar system that use the calends, nonans, and edicts, which are the three major points in each month. They use these three main points of reference in each month to number the day. For instance, calends means the first day of the month. Nonans represent the fifth day of hollow months and the seventh day of full months. And the edicts mean the 30th day of hollow months and the 15th day of full months. Thus, you can see that the record April 2nd as the 4 days before the nonans of April. In contrast, in Babylonian mathematics, their use is mostly practical and scientific. Firstly, it's often used in astronomy because of its nature of the sexagesimal based system, which allow for precise calculation of celestial movement. This system allows for the division of a day into 360 units and a circle into 360 degrees, forming the foundation for modern measurements of times and angles. It helped them to create early models of celestial motion, which Greek astronomers used. And aside from calculation, it also enables the Babylonians to predict a wide range of phenomena of the moon, the sun, and the planets. For example, recording and observing the celestial events such as lunar and solar eclipse. They use this mathematical knowledge and tools to forecast planetary location and solar cycles, thus help aid them in developing a lunar calendar. And by having this calendar, it allows them to better determine the times for religious events, farming, and seasonal activities. Thus, it's clearly shown that the Romans' mathematics is more practical, such as in engineering, trade, commerce, recording and timekeeping. In contrast, the Babylonians used mathematics practically and scientifically, mainly for astronomy and calendars.
Thank you, Joyce. May I share the purpose of Mayan ancient history in mathematics? The Mayans' advanced system, which was decimal base 20 and utilized a revolutionary zero placeholder, was not primarily dedicated to practical commerce or engineering as seen in Rome or Egypt. Instead, its main applications were astronomical prediction and timekeeping. The Mayan mathematical system was inextricably linked to their calendar, allowing them to track complex celestial cycles with extreme accuracy. First one, predicting phenomena, Mayan mathematics and astronomers used their precise calculations to predict solar and lunar eclipse and the movements of Venus and other planets, which were crucial for their religious and agricultural planning. Second one, the long count. Their most famous achievement, the long count calendar, used base 20 calculations with one deliberate irregularity where the third place value was 18 multiply 20 equal 360 to approximate the solar year to measure time over vast periods, emphasizing the cyclical nature of the cosmos. In essence, Mayan mathematics was developed not for terrestrial management, but for a divination and communion with the cosmos, making it one of the most uniquely focused mathematical systems in ancient history. So, I can conclude the civilization represents two major historical approaches to mathematics, practical application and theoretical exploration. Egyptians were purely practical, focusing on everyday needs like record keeping, architecture, and calendar creation to run the state of efficiently. efficiently. Greeks were primarily theoretical, using mathematics to uncover the natural order of the universe. Romans were intensely practical and administrative, using math for trade, commerce, engineering, and meticulous timekeeping. Babylonians were both practical and scientific, utilizing their sophisticated basis positional systems for highly accurate astronomy, predicting celestial movements, developing the lunar calendar, and influencing modern concepts of time and ages. In essence, Egyptians and Romans prioritized using math for running an empire, while Greeks and Babylonians prioritized using math for understanding the cosmos through theory and advanced positional systems, respectively. Friends, we often view ancient history as separate from our modern world, but the systems we have discussed from Egypt, Greece, Rome, Babylon, and the Mayan are not released. They are the invisible bedrock of our modern world. The purpose of mathematics is in antiquity was to manage society, and that purpose remains its primary modern function. The implication of this history will be explained by our panelists, Shermin and Joyce.
Now, without a doubt, Egyptian and Greek mathematics are crucial in the history of mathematics. They basically laid down the foundation for mathematics. Its significance is crucial in the history of mathematics itself. Moreover, its influence could even be seen in modern days. First of all, many of you may not know that Egyptian mathematics fostered the birth of many modern mathematical concepts. To start, it found the concept of unit fraction. The Rhind papyrus contained a 2 over n fraction table as shown in the slide. Ancient Egypt has a special way of representing fractions. They use 1 over n to represent fractions, and this is the foundation of the concept of unit fraction. Second, they found decimal system. The basic of multiplication of 10, which we use in modern days mathematics, is closely related to old Egyptian mathematics. This base 10 system inspired our current counting system and counting logic. For example, 10 mm is 1 cm, 100 cm is 1 meter, etc. This decimal system is also the foundation for our current numeral system, the number 1 to 10, the place value system, and arithmetic. Basically, Egyptian mathematics contributes to the birth of modern day mathematics. It laid down the foundation of the modern data keeping and administration system. As stated by Motion, the Egyptian has a consistent way of distributing resources and their quantity. This systematic framework indicates that a wholesome administration organization exists within ancient Egyptian society. This is similar to the modern statistic and data management that are crucial in modern day government administration. However, Greeks However, Greek mathematicians should not be looked down upon too. Similar to its purpose, Greek mathematics is significant to civilization development from the theoretical aspect. It is significant in modern days due to the numerous mathematical pioneers it produced. For example, Euclid, Aristotle, Plato, Archimedes, and Pythagoras are all ancient Greek pioneers. We all heard of the Pythagoras theorem and Archimedes' story of discovering buoyancy. They each proposed mathematical theories that form the foundation of modern maths. Furthermore, these pioneers not only focused on mathematical field, they are also leaders in philosophy, physics, engineering, and astronomy. Simply say, they form the modern-day academic discipline. Their work deeply influenced the development of our human civilization and becomes the foundation of multiple disciplines. Furthermore, Greek mathematics promote logical and deductive thinking. Different from Egyptian mathematics, Greek mathematics is more abstract. They dive into the theoretical aspect behind the mathematical concept. They pursue knowledge to understand the natural order of this world. The biggest implication Greek mathematics brings fall on its connection. It emphasizes reasoning. It developed the way we think through logic. It helps us to connect information and deduce answers to solve problems. In modern day, this type of thinking is still the general tendency of learning. In conclusion, ancient Egypt mathematics greatly influenced our practical real-life practice, while ancient Greek mathematics greatly influenced our implicit cognition.
I completely agree that Egyptian mathematics is crucial and significant in modern days. However, Roman mathematics and Babylonian mathematics are also significant and have a big influence on modern mathematics nowadays. Firstly, for Roman mathematics is often used in book publication. For instance, the numbering of section of words, the numbering of pages in prefaces, book introduction, appendices, and answers. It illustrates the sequencing and hierarchical relationship to enable learners to better read the content and pages in the book. Secondly, Roman numbers are also commonly used in monarchical titles to show rulers with the same name. For instance, Queen Elizabeth II to show the repetition of names from the same generation that are being used. Uh, Next, when studying science, we can also find that some of the specific names are being labeled using Roman numbers. For instance, Roman numerals are used to label the natural satellites of planet in the order they were discovered, such as Saturn 5 represent Titan, the sixth moon of Saturn. Jupiter 4 represent Callisto, the fourth moon of Jupiter, and more. Besides, Roman numerals are also being used in chemistry. They use it to show the oxidation state of an element or the group number in the periodic table. For example, iron 3, iron 2 sulfate, FeSO4, represent that the iron has a plus 2 charge. While in the periodic table here, the order notation use Roman numerals for groups. For example, group 1 for alkali metals such as sodium and potassium, whereas group 2 for alkaline earth metals such as magnesium and calcium shown in the table here. In contrast, for the Babylonian mathematics, the sexagesimal system, base 60 system is widely used in nowadays. The knowledge of 60 seconds in a minute, 60 minutes in an hour, and 360 degrees in the circles arises from this system. For example, the division of an hour into 60 minutes and a minute into 60 seconds enable us to identify and tell the time accurately. It also allows us to use 12 hours and 24 hours format to tell the time. Moreover, it's also vital in navigation and geometry. For instance, latitude and longitude are determined using degrees, minutes, and seconds when locating location on Earth or navigating at sea or in the air. It's widely used by aircraft and ships, whereby we can determine the location of ships and airplanes through radar. Furthermore, the division of a 360-degree circle also made it simple to compute angles that are fraction of a circle. Equipped with this knowledge, it allows us to measure angles in geometry, trigonometry, and astronomy. It's also applied in engineering, architecture, and surveying, where it provides precise angle measurement, which is essential for building stable and accurate structure. As we can see that the use of these two mathematical tools is very useful until nowadays. We can see that the Roman numerals are no longer used for everyday math, but remain popular for naming numbers, science, and chemistry. Babylonian mathematics is well known for its sexagesimal system, which remains the standard for geometry, trigonometry, and astronomy. Therefore, we must appreciate its significance and value its role.
Thank you, Joyce, for the great sharing. I also will share about how mathematics of ancient history impact modern days. The ancient Mayan civilization significantly impacts the modern world through its advancement in mathematics and timekeeping, particularly in two key areas. The first one, the independent concept of zero. The Mayan independently developed and utilized a symbol for zero, represented by a shell-like glyph, as a placeholder in their numeral system hundreds of years before its widespread use in Europe. In fact, the existence of zero as a placeholder is fundamental to all modern mathematics, including the development of algebra, calculus, and computer science. This achievement demonstrates that complex positional system could be developed independently across different cultures. Second, sophisticated calendrical systems. The Mayan developed interlocking and highly accurate calendar systems, which were used to record history, plan agriculture, and predict astronomical events. Their precise measurements of the solar year were remarkably accurate, in some cases surpassing the European measurements that form the basic of the Gregorian calendar. The principles of their meticulous astronomical observation and recording of patterns are integral to the scientific process used today. Their system for tracking vast period of times, the long count calendar, provides a unique framework for chronological study. Friends, my dear friends, if there is one word that summarizes the purpose, applications, and enduring implication of all these ancient systems, from the Maya zero to the Greek logic and the Babylonian time, that word is foundational. The civilization is not just paved the way of modern mathematics, they handed us the tools and the fundamental concept necessary to build the entire modern world. Why foundational is the best conclusion? Egypt, Egypt, Egypt provided the foundation for decimal systems and applied mathematics, while Greece, a foundation for theoretical thought and deductive reasoning, Babylon, foundation for time-based system and astronomical measurement, Rome, foundation for administrative timekeeping and symbolic use, and lastly, Mayan provided a crucial foundation for positional notation through the independent invention of the zero. Using this word allows you to wrap up by emphasizing the ancient mathematics didn't just influence modern math, it laid the essential base upon which all subsequent scientific and technological development was built. That's all from us. Thank you so much.